Thanks very much, Barry, for the kind words. It's a pleasure being here today. So the last couple of years, I've been teaching a number of course a couple of times on the machine learning and econometrics, and in particular on connections to causal inference. And so there's a couple of reasons for that. One is that I think this, in the computer science and the statistics literature, there have been a lot of new developments, a lot of new techniques developed that are really important, that are potentially very important for economists, and that haven't quite received the attention in the economics literature, in the teaching and the graduate programs as they deserve. I think that's changing now. So there's a number of PhD programs where I know they started teaching some of this material, and I think that'll be increasing over time. I started teaching some of this in my graduate classes. Actually, I saw some of my former students from Econ from Berkeley here. We had some of these lecture notes, but I actually will be this year. I decided to start posting my lecture notes on my website. So as I teach my course this fall, I will be posting them for people who are interested. So actually, I take it the slides here were posted on the website. Is that does anybody actually know? Because the set of slides is far too large for what I'm going to be able to cover today in this hour. But I put a bunch of references at the end, so even if they're not posted yet, I'm sure they will be posted. I'll post them on my own website as well. I realized when Barry was speaking, was introducing me, that I didn't actually put a reference into the book with Don Rubin. So thanks for the kind reference there. But so why am I teaching these things? So one of the things I mentioned is that I think this is just a bunch of important techniques that should just make it into the core of the graduate econometrics programs. These are important things we should know. But another thing is that there's now lots of people doing statistics coming from a very different perspective. The computer science, computer scientists, data science people. And part of this helps connecting with those people and being able to collaborate with those. Barry mentioned I do some work for Amazon at times. And that's a very interesting place from that perspective. There's a huge number of statisticians, there's a huge number of computer scientists. But the last couple of years, they've also hired a lot of economists. I think by now, there's in particular, Pat Byrie has been very influential in hiring these people, setting up an economics group. There's about 100 PhD economists throughout the company, at least in the Seattle headquarters, working with statisticians and working with computer scientists. And it's sort of, if you sit in the conversations there, it's clear. It's clearly a challenge at times when people come from a very different perspective and use very different terminology for very similar questions. But ultimately, when these collaborations work well, they're incredibly valuable, and it's sort of very clear that both the computer science and statistics side, as well as the economics side, bring much to the table there. And so what I want to do in the hour I have here now is talk sort of about some of the methods that tie fairly closely to things we've traditionally thought about in economics, and then talk about two more specific problems where it connects to causal inference. And that's sort of where econometrics and economics brings a lot to the table in solving these problems. So let me skip a couple of these slides. So partly the machine learning literature has been much more about algorithms rather than about modeling and about the statistical properties of methods for estimating things. And so from that perspective, it sort of looks very different. In one of the references I put at the end of the slides, is a paper with the title something like the top 10 algorithms in machine learning. And it's sort of all about trying to find algorithms that solve particular problems and then comparing how they do in practice, rather than thinking about the formal properties. And it sort of gives you a lot of freedom. There's no rules what you're allowed to do, what you're not allowed to do, and there's not the kind of focus on asymptotic properties that often makes it very difficult to come up with new methods in econometrics. But it also sort of implies somewhat of a lack of discipline where the other parts of statistics and econometrics have been much more formal. The setting often is one where we have very large data sets. Sometimes this may mean many units, but sometimes it may be many predictors. So obviously at Amazon, we know a lot about many individuals who purchase on the platform there. But we also know, so we have many individuals, but we also know a lot about each of these individuals that we can use to predict and show them various products that they may want to purchase. One big difference with the econometrics and economics literature is that there's very little emphasis on causality. Many of the methods are very specifically targeting prediction and fit of the models. And that's an important distinction for a number of reasons. One, it makes some of the problems much easier. It's going to be much easier to compare methods in terms of predictive power than it is comparing methods for causal effects. Ultimately, with causal effects, we never actually see the truth, and so it's very hard to see whether one algorithm or one method performs better than others. Whereas if we are interested in prediction, we can often use out-of-sample cross-validation to validate and rank methods. Another complication is that often the terminology is very different for the same concepts. The machine learning literature talks about training instead of estimating. They don't talk about covariates or exogenous variables. They talk about features. And so there's many cases where a lot of it is just a matter of translating things we know into the things that come up in the machine learning literature. Now, so there's a couple of key components to these algorithms. So as I said before, there's a big role for out-of-sample cross-validation. Traditionally in economics, we use a single sample for estimating a model and possibly doing tests on the properties of that model and assessing asymptotic properties. But in the machine learning literature, there's a big role for the cross-validation. And so that's sort of very much tied to the focus on prediction. For predictive problems, from just a single realization, we can get an unbiased estimate of the conditional expectation. So suppose we have data on a pair of values y and x. We're interested in predicting y given x. So the best predictor is just the conditional expectation of y given x. But for any value of x that we observe, we actually get an unbiased estimate of that object, namely the outcome for that particular unit. And that's not the same for causal effects. even if we have data on lots of units for a particular value of x, we can't directly get an unbiased estimate of what the causal effect is. We never know for sure what the causal effect is. And that makes it very hard to compare methods, compare different algorithms that both try to get estimates of causal effects. And we'll see that a little bit in one of the examples I want to discuss, where we're directly looking at causal effect, that often requires us to modify these methods. Second component is that often we look at very rich models. We're often doing what used to be referred to as nonparametric regression or nonparametric density estimation. And so there's a lot of emphasis on regularizing these estimates, these estimators, to avoid overfitting. And so, again, here, where traditionally in econometrics we would use plug-in methods, we would try to use the data to estimate the unknown functions and then find the optimal amount of regularization, say the bandwidth in a kernel estimator, find the optimal amount of regularization through these plug-in methods. In the machine learning literature, this is almost exclusively done by cross-validation methods, where you put part of the sample aside and you see how well the methods work out of sample and use that evidence to figure out how much to penalize overfitting. A third feature that receives much more emphasis in the machine learning literature than in the econometrics literature is that of scalability. In the end, we need methods that reliably handle very large amounts of data. And so traditionally in econometrics, there's been a lot of structural work where we estimate relatively complex models that directly allow us to answer very involved policy questions. But often those methods take a lot of time computationally. They don't scale very well. They don't work with very large samples. And so they don't really fit a lot of these modern problems. Now, let me get into sort of a little bit more detail for some of these methods. And so what I want to focus on most of the first half of the rest of the first half of this talk is supervised learning methods. And so there's two settings there, classification. The first one is classification, where we're interested in predicting a discrete, unordered outcome. Because traditionally, people may have used multinomial logit or conditional logit or random effects logit models. So here, the setting is one where we observe these unordered discrete outcomes y. We observe a set of covariates or features x, and we're trying to find a function that not so much estimates the probability of a new observation having a particular value for the outcome, but that assigns a new observation to one of those categories where the new set of the covariates or features is drawn from the same distribution as the set of observations we observe. And so there's been an enormous amount of progress in that literature. The automatic reading of zip codes now is incredibly effective. And so here, this is a problem where there's clearly no causal question other than possibly people changing their handwriting, knowing that it's going to be read by a computer and that it's important for a computer to write in a particular way. But in principle, this is a pure prediction problem, and there's sort of more complicated versions of this. But some of the methods we'll be looking at sort of work for those problems. Even more familiar from the econometric literature is the regression version of this, where we have a continuous outcome, and we're just trying to predict the conditional mean of y given x. for new observations drawn from the same population. And so what we traditionally would have done in the econometrics literature and what we typically teach in econometric sequences is using kernel regression methods, where we just weight the observations by the closeness of the axis to the particular axis where we're trying to do the prediction. But it's sort of well known that doesn't really work very well in settings where the axis is high dimensional. And so what the machine learning literature here has focused on is trying to find methods that work well even in settings with high dimensional axis. And the emphasis has been much more on whether these methods work than on what their asymptotic properties are. For kernel methods, we've long ago established what these methods are consistent, these methods are asymptotically normal, and that's often much harder for these more recent machine learning methods, but it hasn't really been the priority for them. And so let me then kind of talk sort of more specifically about a particular setting where we're going to look at linear regression, but in settings with a possibly very large number of predictors. And so in conventional settings where we have a few covariates, then just doing ordinary least squares is a very effective and sensible method. But it doesn't really work very well if there's a lot of covariates. So many years ago, when I was a junior faculty at Harvard, Zvi Gavrilec was very influential there. I remember him, I guess he has an agricultural economics background as well. But I remember one of his favorite sayings was that you should never really trust OLS with more than 5 regressors. And now in these modern settings, we have this linear model set up, but we may want to do it with billions of observations. We may have millions or also billions of regressors. And so it's clear that simple least squares estimation isn't going to be very effective there, isn't going to have very good properties in terms of prediction out of sample. And so what we need is some kind of regularization. We need to somehow constrain the estimators to deal with the fact that there's too many covariates to be able to predict outcomes accurately. So here's a second quote from Vapnik, who developed the support vector machines methodology, which is a very prominent methodology for classification, where he says that regularization theory was one of the first signs of the existence of intelligent inference. Vapnik is not a particularly modest person, so one of his other, apparently he told some people at some point that when they were complaining about the fact that he wasn't always very generous with other researchers, he said, well, 300 years from now, they're not going to remember whether I was a nice guy or not. They're going to remember my work. And certainly his work has been very, very impressive. So how do we do regularization in this simple setting? In the end, we're going to shrink some of the estimates towards zero. And we can do that in a couple of ways. We can shrink estimates continuously towards zero. We can limit the number of non-zero estimates in what is known as a sparse representation. So the idea is that in the end, we select some of the covariates that are important for predicting y and set the coefficients for the others equal to zero. That's sort of a very important concept. And it's often not really clear whether sparsity is plausible. It's also often not clear whether sparsity is important. If we're just doing purely prediction, if you do purely a prediction exercise, it may not be important whether a particular coefficient is equal to 0 or equal to 0.001. And so there's an important choice here between methods that do lead to a sparse representation that often is nice in the sense that you can actually look at some of the covariates. You can see which covariates are important, or look at methods that shrink estimates more smoothly towards 0, that are not as easily interpretable, but that may do it just as well or better in terms of prediction. And so there's a very interesting discussion there in what is a great textbook by Hastie, Tibshirani, and Wainwright about the sparsity principle, where they argue that you should use a procedure that does well in sparse problems, because if the problem actually is sparse, then these procedures are going to do well. And if the problem is not sparse, nothing is going to do well. I don't find it a completely convincing argument. I think in social science, typically we have problems are not sparse in the end. Whatever possible predictors you can use, they're always going to be correlated to some extent with the things you're trying to predict. And it's not always clear that you can separate things into a set of covariates that is important and a set of covariates that is not important. And so shrinking more smoothly may well work better in some of these cases. And so I do think it's important to think about what the methods work in both settings. So the simplest cases of shrinkage is just finding methods that select just the subset of the regressors and then do least squares on the subset. And so you can implement that through putting a penalty term that is linear in the number of non-zero coefficients. That turns out to be a very difficult thing to do in practice, particularly in large settings. It also has conceptual problems, namely, if you look at for the best single covariate, that may not necessarily be included in the set of the two best covariates. It could be that x1 is the best single covariate for predicting y, but if you allow for two covariates that x2 and x4 do better together than x1 with one of them or x1 with any others. And so there's a non-monotonicity to this set that is somewhat awkward. Second problem, and that's probably the most important one, is it doesn't really work very well for large values of k. In principle, you need to go through very large sets of covariates, and that quickly becomes impossible. The sort of greedy versions of this, where you do things sequentially, going back to old stepwise regression methods, but they don't work particularly well in practice, and certainly are not the most popular methods these days. Now, sort of starting from the other side, another old method is ridge regression, where you start with the least squares estimator, but you shrink it a little bit smoothly towards 0 by implicitly putting a prior on the betas that is centered around 0 with some variance. And so now, irrespective of the dimension of the set of regressors, you always get a unique solution for what is essentially the posterior mean, but here it can be viewed as a frequentist estimator, where you regularize by using a quadratic penalty function. Now, the third method I want to discuss here is the most prominent these days in this literature. This was developed by Tibshirani, the least absolute selection and shrinkage operator, or LASSO. And so there, you start with the least squares objective function, but now you add a penalty term that is proportional to the sum of the absolute values of the betas. Whereas you can characterize ridge by having a penalty term to the least squares objective function that is proportional to the sum of the squares of the betas. Here, Lasso uses the sum of the absolute values. And so at some level, that's a very minor difference. You can implicitly interpret this as using a prior that instead of being normal the way it is for rich, it's Laplace prior that has tails that vanish more slowly than the ones for rich. But in terms of that prior distribution, it's really very hard to make a strong case that using Lasso makes more sense than using rich. We don't really have any reason to think that the Laplace prior is more plausible than a normal prior. So why? And so, but yet Lasso has sort of received an enormous amount of attention. Here's a quote from Andrew Gellman from his blog, where he wrote that Lasso is huge. This is a long time before the election. But so why is that the case? At some level, it looks very similar to rich and even subset selection, where the only difference is in the way the penalty term is chosen, where rich uses something that's linear in the sum of the squares of the betas. The subset selection just counts the number of non-zero terms, and Lasso uses something that is linear in the absolute values. So here's a figure to kind of illustrate what's going on there. What subset selection does is, let me just move this. That's the dashed line. Depending on what the least squares estimator is, if the least squares estimator is very small, the best subset selector estimator is going to set it equal to 0, and then at some point it switches back to the value for the OLS estimator. Rich just swings everything towards 0. Thank you. It swings everything towards 0 more smoothly, and Lasso swings things to 0, exactly to 0 for small values, and then it's linear, but it doesn't go back to the least squares values. Now, what makes Lasso interesting is that it combines this smooth shrinkage with this exact zeros feature. And so here's another figure to try to illustrate that. In these two figures, you see the least squares estimator in a two-dimensional space, and the ellipsoids that capture the confidence intervals. And so what Rich then would be trying to do is look for the point on one of these ellipsoids that is closest to 0, where closeness is measured in terms of the distance to these circles around 0. So that's coming from having this normal prior on the betas. Lasso, on the other hand, tries to look for the point on these ellipsoids that's closest to these, well, they should have been squares, but they're diamonds here. And so occasionally, the closest point will be exactly one of the points where one of the coefficients is 0, or it could be on one of the line segments. And so it allows for the possibility that one of the estimates is exactly 0, but it also allows them to be different from 0. And so this has become a very popular method, and has made considerable inroads in the econometrics literature. There's been a lot of work by Belloni, Chernosikov, and Hansen with a very nice paper in the Journal of Econometric Perspectives a couple of years ago. You see a lot of references to the economics literature. And so what's made it so popular is that it's a very natural way in the end of, and a very computationally convenient way of dealing with many covariates, where traditionally we would have often just chosen a small subset of regressors in somewhat ad hoc ways. Here there's a systematic way of choosing the regressors, but then we can use many of the standard methods for interpreting the results. And compared to ridge, where you can't really look at all the coefficients in the end, if you're doing this with thousands of regressors, with lasso, it often selects just a very small subset so that you can actually see which of the covariates matter. For inference, it is also very convenient because under some conditions, which are not necessarily particularly plausible, but at least give some justification for doing this. Under some conditions, you can get standard errors, ignoring the selection that has gone into the lasso estimator. So you can ignore the zeros and just focus on the least squares estimators for the non-zero coefficients and get standard errors conditional on that set. Now there are sort of a couple of less attractive features of this. One of them is that lasso compared to ridge doesn't work particularly well in settings where the regressors are very highly correlated. If you suppose we have two regressors that are in fact perfectly correlated, if we were to do, suppose we're running a regression with only two regressors. Suppose these two regressors are actually identical, so we can't separately estimate beta 1 and beta 2 by least squares. Ridge would have no problem with that. It would just split the difference and estimate both approximately equal to the average of the true values. Lasso, on the other hand, would try to set one of them equal to 0, but clearly in this case, where the problem is completely symmetric in x1 and x2, it would be indifferent between setting beta 1 hat equal to 0 versus beta 2 hat equal to 0. And as a result, it sort of more generally, it tends to be somewhat unstable in settings where the covariates are very highly correlated. I sort of already mentioned this part about this being a Bayesian estimator. So let me now skip ahead a little bit and talk about one other set of methods. And so here's a set of methods that hasn't made quite as much of an impression in the economics literature, but that in the end is a very effective set of methods for doing non-parametric regression, and it's very widely used in the machine learning literature and in the private companies. At Amazon, we use these methods very widely. I now realize there was something I wanted to mention in the introduction, sort of about. Let me do it here. So one of the places where these interactions with the computer science and statistics people and economists are very important. In the end, at a place like Amazon, we're almost always interested in causal effects. And so for economists, it's just very natural to worry about endogeneity issues. And so when we look at price and quantity data, we typically, we're often interested in estimating demand functions. We're interested in trying to get price elasticities. And it's just incredibly hard, sort of given their background, for a lot of the computer scientists to understand that you can't get a demand function by just regressing quantity on prices. That no matter how many covariates you put in there, how many more things, we have a lot of those things we can put in there, but how many of these things you can put in there, it's never actually going to be the demand function. And you just need to think about those things in a very different way. And for economists, that is just very natural. That comes very naturally, because that's sort of what we've been doing from the start. At some level, econometrics was started when people started worrying about supply and demand. The idea that you would think of prices as completely exogenous doesn't really make any sense. But other disciplines don't start from that perspective, and so they have a very hard time seeing why you wouldn't just try to predict quantity given price. And it would also, as a result, it wouldn't really have any problem with finding that in the end the demand function would look flat or would be increasing, because there's no concept of what the demand function really should be trying to capture. And it's sort of in those interactions that economists can contribute an enormous amount, and it's sort of harnessing the power from a lot of these machine learning methods in combination with the economic insights that is one of the big challenges. Now, sort of going back to the second method I want to talk about here, these regression trees, and again, they're actually very similar to things we used to think about and do, namely in this case nearest neighbor estimation. The idea with the regression trees is to partition the covariate space, the feature space, into subspaces, where within these subspaces we just estimate the regression function as a constant, just by averaging the outcomes for those units. And we do the partitioning is done sequentially, where we do it one covariate at a time, always trying to look for the split that is the most effective in terms of reducing the sum of squared deviations from the estimated regression function. And so, starting with the point where there's a single subspace, we would be estimating the regression function as a simple average, and then we would look for covariates. We look over all the covariates, we look over all possible thresholds. We would look at the implications of splitting the data at a particular point, estimating the regression function now by averaging things within these two subspaces, and then finding the covariate and the threshold that minimizes the sum of squared deviations over all these possible splits. And that's obviously a very simple way of estimating a regression function, but it's compared to the way we traditionally did nonparametric regressions, where we chose the bandwidth and fixed a lot of these things in advance. This is sort of a very adaptive way where you split things more, where there's more to be gained, where there's more data, where the regression function is more nonlinear. And as a result, these tree methods and variance and extensions thereof have been incredibly effective as sort of out-of-the-box, out-of-the-shelf methods for estimating regression function compared to, say, kernel methods of the type that people would use traditionally. And so, obviously, every time you keep splitting a subspace, you're going to improve the objective function, sum of squared residuals. And so, in order to regularize that, people typically add a penalty term that is linear in the number of leaves, and then use out-of-sample cross-validation to find the optimal amount of regularization, and use that to come up with an optimal tree that is not overfitting too much. Again, let me not spend too much time on the details here, but to get the penalty term, we do the out-of-sample cross-validation and then find the optimal tree. There's sort of one early extension was to not just grow a tree till to find the optimal tree, but possibly initially grow it larger than necessary, and then go back and prune things to avoid getting stuck early on with an estimated regression function with a tree that is too small because it couldn't anticipate the interactions between variables. And so here, well, this is probably not going to be very visible from the back. So, doing this on a particular data set, and there's sort of some details in the earlier part of the slides, with about 120 regressors, and where I tried to predict earnings data based on lagged earnings and a whole bunch of other variables. Just doing OLS on the full set of covariates gave an estimated squared error on a test sample, so checking out of sample how well these methods work. There was almost twice what it was for Lasso, and with the tree doing slightly worse than Lasso, but still far better than OLS. And so these methods typically just do much better in terms of prediction. Now let me skip ahead and get to some of the causal things. Actually, sort of one final comment there is another big insight from this literature is that often any particular method for doing prediction doesn't work as well as model averaging, as finding some ways of combining these methods. So here in this case, instead of doing either OLS, doing Lasso, or using this tree, you could look for a combination of these methods, and in this case, that does only slightly better than Lasso, but in many cases, using lots of prediction methods and then finding a way of combining them leads to substantial improvements over any of the individual methods. Okay, so now let me get back to the causal part. And so here I'll be talking a little bit about some joint work with Susan Athey and a new colleague of ours, Stefan Wager, who just finished his PhD at the statistics department at Stanford. And so here, there's sort of an old setting from the perspective of the causal literature. We're interested in estimating average treatment effect. We're willing to assume unconfoundedness, so that we have meaning that we have a rich enough set of covariates that conditional on those covariates, the assignment can be viewed as good as random. And so I set it up in this potential outcome framework. We're interested in the average effect y1 minus y0. Here, actually, I'll focus on the average effect for the treated, so it makes the exposition slightly easier. We only see the realized outcome, either y0 or y1. We're willing to assume unconfoundedness, and we're assuming that there's overlap in the covariate distributions so that we can actually implement that. So the large part of my book with Ruben focuses on this problem in settings with a relatively modest number of covariates, and there's a lot of methods that we understand, where we understand how well they work and which ones work well in what particular settings, and so particular subclassification with some regression adjustment within subclasses works well, where we first estimate the propensity score. The doubly robust methods associated with the work by Jamie Robbins works well in that setting. But the question here is what to do if we have a lot of covariates, and so and we maybe thinking about settings where we have a couple of thousand observations, and we may have hundreds of covariates, or we may even have thousands of covariates. So we can't directly use any of these methods. And so we could, one thing we could do is directly import some of these methods. So there's some work by McCaffrey, Ridgway, and Morrill where they use propensity score methods, particular propensity score matching, and the only modification really is that they estimate the propensity score using machine learning methods, and they look at three type methods, in particular random forests, as well as lasso type methods. Belloni, Chernozikov, and Hansen tried to estimate the conditional expectation of y given x in the control group using machine learning methods, focusing particular on lasso type methods. But the method I want to focus on here is sort of a combination of direct balancing as well as regression adjustment. And let me get to the so what we're trying to do here is to find to adjust. So we're going to take two approaches to the adjustment. One where we're trying to find weights for the control group to make it look like the treatment group, and we're doing that in a way that works even in relatively high dimensions by not directly trying to estimate the propensity score, but directly trying to estimate the weights that may have a lot fewer parameters than the propensity score. That in itself is not going to give us enough bias reduction, getting the weights to get all the covariates to match is difficult in settings with high dimensional covariates. And then what we do is combine that with estimating the regression function, combining that with estimating the conditional mean of y given x in the control group, where we use regularized regression. And in particular, we use elastic net, which is sort of a combination of lasso and the penalty term from ridge regression. So it has some of the benefits of both ridge and lasso. And we combine that with the weighting. And neither simply doing the regression with regularization nor doing the weighting with regularization works well. But it's sort of the combination of the two that tends to work much better in practice. Now, let me then kind of briefly mention the last sort of problem where, again, we're kind of combining some of these machine learning methods with a specific focus on causal effects. And so so much of the literature on causality has sort of focused on estimating average treatment effects. But in many cases now we're trying to do more targeted things. We're trying to find subpopulations for which interventions are particularly effective or particularly problematic. And obviously in a lot of the industry applications, there's also a lot of interest in trying to figure out whether particular campaigns work for some subpopulations rather than the other. And so we're looking here at a setting where we have experimental data, and now we're trying to find subpopulations that differ in terms of their average effect. And so the three methods are a very natural way for doing that, the very natural way for trying to construct these subpopulations. But the problem is we don't see the causal effects directly, so we can't directly estimate these trees. And so what we do here in this approach is trying to modify the tree methods, modify the objective function there so that it looks for average treatment effects. And so let me just get to the application here. This was data that Susan had used before. So this was so this doesn't look particularly good, but so let me just talk you through it. So this is data from a search engine from Bing, and so the question was, how much do you hurt a particular? So you search for a particular item, the algorithm comes up with a number of answers, and they typically put their best answer at the top. The question is, how much would you hurt the rate at which people click on that if you put the best answer somewhere else? If you put something to favor your own objectives there. So the question is, what is the causal effect of putting something high relative to or low on the page? And we know that the things that are at the top of the page get clicked on more, but that may be partly because they're the right answers rather than because they were put at the top. And so they did these experiments, and they found that if you move something from the top place to the third place, that reduces the click-through rate by about 13%. But it's very unlikely that that's the same for everything. That may differ a lot by the type of query you're doing. And so using these methods, you find that if you're looking for a particular image and you're looking for a celebrity, it doesn't actually make all that much difference where you put the answer. If you're looking, say, for Britney Spears, for a picture of Britney Spears, it doesn't matter whether you put it in the first place or the third place, because you know what you're looking for anyway. But on the other hand, if you're looking for a query that is really about some information you're trying to get, then it can make a huge difference. So if you're trying to look for instrumental variables or machine learning, then putting something in the first place or the third place makes a big difference. And so that makes a lot of sense. And so here these methods allow you to kind of, in a principled way, trying to find these subsets where particular treatment effects are bigger or smaller than for other units. So let me stop here. I realized I've gone through these slides very quickly, but they'll be posted, and there's a bunch of references at the end there for people who are more interested in this. And as I said, also we'll be posting my lecture notes this coming quarter on my webpage for people who want to see more of this.